nanoparticles. There's more evidence that Alzheimer's, for example, is linked to something called an amyloid fibril. That's a naturally occurring nanostructure that's not normal in the body. So these nanomaterials and nanoparticles, we're responsible, but we're also, nature is responsible for them. And we really need to sort out where that difference is and which ones are beneficial without being toxic to us. Diesel engines over the road right now put out about 40,000 tons per year in nanoparticulate. Now regulating over-the-road diesels. Next is going to be off-road diesels. Trains and ships, about 32,000 tons per year of nanoparticulate. So those industries are starting to come under regulation. But we do many things that we impose these nanoparticles on ourselves. If you have a gas stove, every time you light that burner with the spark, you're creating an abundance of carbon nanotubes. And then as long as that flame burns, the flame is glowing micro and nanoparticles being put out into the environment. A pure wax candle, and all these sources, candle, cigarette, frying meat, a gas stove, a vacuum cleaner, ironing a cotton shirt, all of those things put out nanoparticles. So yes, we need to look at this very, very carefully. But we have brought a lot of that nanomaterial upon ourselves, not knowing. And that may be one of the sort of saviors of this whole debate, is maybe now we're becoming aware that what we've been doing for generations and generations maybe hasn't been so good to begin with, and we just now have the technology and the foresight to look and see what has happened. So there are a lot of studies being done in the effects of nanomaterials on the body. The one slide I went through very quickly, some work that's being done in Dr. Blau's lab looking at, for example, cerium oxide nanoparticles. I told them I really don't want to know that, because as a youngster, an amateur astronomer, I'd grind my own telescope mirrors, and cerium oxide was the polishing material of choice. And we'd have buckets of cerium oxide laying around, nanoparticles laying around. So there are a number of efforts beginning to look at this. Unfortunately, it can be this double-edged sword. Is industry going to investigate it? Well, they certainly know there could be potential liability there, but they don't want to know too much because it could put them out of business. So just how much is good to know and when is it too much? So the bottom line from the National Toxicology Program. Should we panic? No. This is their opinion. Should we panic? No. Should we be concerned? Yes, absolutely. Is there a quick answer? There's not going to be one. Do we know which questions to ask? Yes, but it's going to take very systematic and timely research in order to answer those questions, because now we're dealing with living systems, and those are tremendously complex and have many, many different processes going on. So where do we go from here in conclusion? These are my sort of takes, my ideas of additional places where nanotechnology could become of value. I mentioned that one, and that's more accurate disease diagnosis earlier on. Unfortunately, there are too many false negatives and false positives, especially in the ICU where time is of an essence. We need better testing. We need more positive testing. You know, the human genome, they're saying that the next disruptive technology will be the $1,000 genome. Right now it's $10,000. So that you can know everything there is to know about yourself for $10,000. To get from $10,000 to $1,000. So the market isn't there for $10,000. It is there for $1,000. To get from $10,000 to $1,000 is not in any way hardware oriented. It's computing oriented. There's such a massive amount of information. How do you go about analyzing and storing all of the data when you sequence those 3 billion base pairs in the human genome? There are a lot of ethical problems. Suppose you take your 4-year-old daughter in and say, there may be signs of autism. And in the process, they discover maybe a predisposition for breast cancer. What do they do with that information? Are they bound to give it to you ethically or to not reveal it? So there are a lot of philosophical questions that the medical community is starting to look at. Is we know all these things now. What do we do with it all? Those are problems. Therapies that will attack the disease and not the body. You get a shot, it's systemic effect on the body. Let's attack the malady very locally. Some of that's being done, some of it's been approved. MD Anderson Cancer Center is using gold nanoparticle therapy to thermally treat cancer tumors. That's FDA approved. Safe drinking water. A third of the world's population suffers from not having clean water to drink. 13 million people a year die from waterborne infections. Nanotechnology is capable of creating clean water. It can take out bacteria, particulate. It can do that. It's not easy and it's not cheap, but it can do it. And cleaner surfaces. And there was one of the morning shows just the other day, somebody is proposing that we no longer shake hands. We bump elbows. Because so much disease is spread, viruses and so on, spread by shaking hands. So everybody should bump elbows now as a way of saying hi to each other. But, surfaces. We all touch surfaces, and then I touch it, and you touch it, and everybody touches it. Is there a way to make those surfaces naturally antibacterial? So these are perhaps some of those killer apps, as they say. Lately with E. coli and salmonella, I've seen, all right, now how do we create plastic wrap that will change color or give some other indication if there's E. coli present, if there's salmonella present, whatever is present? How do we do that for a fraction of a penny a square yard? That would be a money maker. So, the future is what we make of it. It's not on any particular path. I always thought Terminator was the movie, the use of technology. If anybody has any questions, I'd be happy to try to answer those, but that concludes my remarks. Yes, sir.
Worldwide, would you say which countries have made headways in this area specifically? I know the United States has put money in it, but who are the leaders really worldwide in that field?
There is, in any particular area or just in general?
Generally speaking.
In general, the Japanese certainly, they are doing a lot in the area of medical support technologies, which may not be the core nano itself, but a lot of instrumentation and diagnostic technologies. The Japanese have done a lot there. Denmark comes to mind. I get publications from them. They're doing a lot of work. Europe sort of in general, but Europe's got problems now just like everybody else. But when you start, looking at specific areas, some of the leading advocates for limiting nanotechnology are in Australia. There's a large movement in anti-nano in Australia going on. The U.S. is large in terms of absolute numbers. There's still a lot of venture capital investment going on. In the life sciences area, there were some venture capitalists at that conference last month, and they're saying in that area about the average venture capital investment is about $20 million into small startups right now. So in the health area, it's wide open. So whoever is going to take that and run with it, I think, so long as people are willing to know everything that technology can tell us, and I'm not sure we are, I think we are very well poised in the U.S. because of our history of medical research and university, the magnitude of university infrastructure that's here.
In the healthcare and life sciences, did FDA come up with any guidances for new technologies, or is still they're evolving, or what's the take of the agency on all of these?
I was at an orthopedic conference back in the summer down in from here up in Warsaw, Indiana, you know, the orthopedic capital of the world. And for new orthopedic technology, the FDA, and I'm probably getting my numbers wrong, so take this with a grain of salt, but I thought it said that new technology, well, not disruptive technologies, but what they call 501K or 510K.
510K.
About 90 FDA working days. That's where they're supposed to be able to
Right.
approve those. Well, even on their own website, that's at, I think they're up over 180 to 200 days. So they are overburdened with everything that needs to be done. As far as these biomarkers, to my knowledge, there are only several of those that have been FDA approved. So you might say, well, why do you have to FDA approve a molecule? Well, you know, is that a legitimate marker of a legitimate problem? Because anybody could be out there selling snake oil, you know, and so I think the regulatory burden on this is going to get only worse, because the amount of information and research that's being done is so voluminous. Everybody's chasing this now, and I think the approval backlog is going to be a serious problem. There are going to be technologies sitting there ready to go, and all you know, they could wait years on approvals.
So we're shortchanging ourselves here in this country by doing that.
Yeah, in a way. Yeah. You know, the FDA certainly serves a very necessary role, absolutely, but they need to be able to keep pace with the potential benefits of what's being brought to them before they kind of valve it out into the public domain. So, yeah. Yes?
You talked about the diagnostics for with your biomarkers. What I was wondering is what progress has been made in the treatment of diseases. If you can identify certain cells through the biomarkers, there ought to be a way to quickly then attack and selectively destroy those cells. You know, and we're thinking about the obvious ones clearly. So
Yeah.
what progress has been made in terms of commercial applications there?
Well, biomarkers, you know, those the kind we're looking at are extremely small molecules. You can think of them, and Eric, correct me if I'm wrong, I'm going to put this in engineering understanding. We're looking at what are referred to as microRNAs, which is take the DNA helix, break it in half, and take a little tiny piece of that. It's not chemically the same, but it would structurally be somewhat similar to that. And those are only maybe 20 of those base pairs long. Well, there are pieces of the human genome that are being very, very heavily studied. And those are two of the genes for breast cancer. Probably the two most heavily studied genes in the genome so far. And this came from a medical doctor I recently talked to, that there's a company that has been studying those genes, the BRCA1, BRCA2 genes, and they find mutations. They find on the order of 100 new mutations every week in that gene, in their work. The vast majority of those, they feel, are benign mutations. You know, it's not going to make a difference. It doesn't indicate anything. So there are several of those genomic type markers that are becoming more and more accepted as good indicators or good potential indicators. Are there any that are absolutely the indicator? I'm not the life science person. I'm going to have to defer to the life science expertise. Are there any positively defined markers?
I think we're getting there. I mean, the animal literature is a lot farther than what we see in humans, but we're not quite there yet. And as far as, you know, the promise of nanotechnology for that silver bullet of delivering a drug specifically to a tumor, I think there's some very interesting data in the animals once again. But to my knowledge, in humans, I think it's just in the very beginning stage. But actually, we have another, Dr. John Schloss from the School of Pharmacy. He might also give a comment on this.
Well, one of the things we didn't hear about, which is particularly interesting in this regard, are multifunctionalized nanoparticles, where you have recognition elements linked to together with therapeutic substances.
Yeah.
So there's a lot of mileage left in terms of where we're going to go with this.
Yeah, certainly.
Theranostics, I think they call it.
So, Dr. Craig, you said about orthopedic implants with titanium nanotubes. So, how long does it's gonna take to use it in the medical application?
Yeah, I said I was going to comment on that. Okay. So far, those have not been presented to the FDA. Those are still under studies. We have done some work that we're about to publish that have shown that, I showed you that one picture of a bone screw that had nanotubes. In an actual application, that bone screw would be inserted one time. That's its use. We've inserted it into bone simulant. We've inserted it and removed it twice, and the nanotube survived. So did one nanotube get brushed off that surface? We cannot say. We cannot say. So we're beginning to do work now where we are growing various types of cells in a nanotube-laden broth to look at how those cells might respond to loose nanotubes in the environment. We know certainly from a respiratory standpoint, they're no good. You don't want them. From an internal point of view, there are indications that the body will immediately encapsulate them with collagen and will more or less confine them. But I think that was just one paper that came out about 6 months ago. It's only one study, and that was in an abdominal animal model, not in a joint. Now, just to be certain here, with all the bad press that orthopedic implants are getting now, with all the advertisements on TV and recalls and all that, we are not advocating in any way, shape, or form of having these on surfaces that would see wear or articulating surfaces. No. These are on the portion of the implant that binds and interacts with bone to form a stronger, longer lasting bond between the bone and the metal. So no. How long will it take? Work is being done. There are only a couple of groups in the country that are looking at these. We're one of them. But again, we can only do it so quickly. We can use lots of good grad students, but we can only look at that so quickly. But we're progressing, at least now at the cellular level, and we'll be moving up. We have a partner who will be moving up to the animal level probably in the next year or so, possibly a year and a half at a research hospital. Again, that's got a long road to hoe, but it's showing promise. The tubes are strong. The beauty of that is now the titanium is primarily coated with a secondary material. Hydroxyapatite is like cement. It's a calcium material. Well, that bond strength is very low, and that's part of the failure. Is that hydroxyapatite breaks down and delaminates from the titanium over time. These nanotubes, and I didn't have a chance to talk about it, are not a deposition process. That's the bulk material. We're removing material to produce those structures. So those nanotubes maintain essentially the properties of the bulk native material. Now they've been chemically changed slightly, but we've actually done mechanical compression testing on single nanotubes real time inside a transmission electron microscope watching it fail. And we've gotten all the stress strain data from that, the structural behavior of that nanotube. And so that's one advantage there is titanium is a very strong, tough material. And most of that property is maintained in those nanotubes because it's the bulk, what's left of the bulk material. So that's why we think it's got promise.
I have one more.
Sure.
So you said to make these orthopedic implants, you have to heat these nanotubes so that the cells will go and adhere to the tubes.
Well, they will grow faster
Okay.
on the heat-treated tubes. So the cells grow slowest on bare titanium, then they grow much faster on the amorphous as fabricated titanium nanotubes, and then grow much faster if we heat treat these nanotubes. What happens when we heat treat the nanotubes, they become crystalline. They change their physical structure into a crystalline material. Now, is that the reason that the cells like them better, or the reason it's more hydrophilic? We're still trying to figure that out. It could be the surface chemistry, or it could be the primary structure of the nanotube. We're still looking at that, trying to figure it out.
Actually, my question was, like, if you heat them, how can you implant them in the body? Like, how can you maintain the temperature?
Oh, no. This is part of the manufacturing process.
Okay.
You know, just like with any other metal that you might heat treat to change its properties, we would do that.
Okay. Thank you.
And then I didn't show it. We're now in the process of, in a single step, creating what we feel are antibacterial nanotubes, because that's a huge problem with orthopedic surgeries, infection, post-op infection. I thought I saw somebody else was going to ask.
Thank you very much.
Please fill these sheets out, just put them here on the back table, because this has to be turned into NASA. This is a NASA grant we have to be able to continue to get NASA grants for this thing. Things we need to at least be able to say good, bad, or Dr. Craig.
Sure.
Thank you.
She may have figured that was it.